Chair of the Department of Natural Language Processing, Mohammed bin Zayed University of Artificial Intelligence, in addition to being a Melbourne Laureate Professor in the School of Computing and Information Systems, University of Melbourne. Furthermore, he has completed a BSc, CS Maths and BA Linguistics Japanese at the University of Melbourne in 1995, and a Masters of Engineering CS and PhD CS at the Tokyo Institute of Technology in 1998 and 2001 respectively. He joined MBZUAI at the start of 2022, prior to which he was based at the University of Melbourne for 17 years. His research had been funded by organizations including the Australia Research Council, Google, Microsoft, Xerox, ByteDance, Seek, NTT, and Fujitsu, and has been featured in MIT Tech Review, IEEE Spectrum, The Times, ABC News, The Age, Sydney Morning Herald, and Australian Financial Review, to name a few. He is the author of well over 450 peer-reviewed publications across diverse topics in natural language processing and AI, with over 20,000 citations and an H-index of 70 Google Scholar, in addition of being an ARC Future Fellow and the recipient of a number of awards at top conferences. Ladies and gentlemen, it is my utmost honor to invite on stage Professor Timothy Baldwin.
Thanks for the high energy introduction, and a great pleasure to be here on campus at UCSC and to be able to interact with some of the brightest minds in ICT in Sri Lanka. It's my first time here and I'm very excited. Okay, so today I'm going to talk about a topic which was set up very ably by our first keynote this morning on fairness and safety in artificial intelligence, with a particular bias towards my own home discipline, NLP, or natural language processing. Before I do that, if you will humor me, I will present exactly 2 slides on MBZUAI, the Mohammed bin Zayed University of Artificial Intelligence, where I've been based since the start of last year, as was mentioned in the introduction, just to give you a little bit of context for the university. And so when, as I hope will be the case, we interact with you at the stand we have out in the exhibitors area, you'll have a bit of context for what we're all about. Hey. Sorry, maybe I don't want to use the clicker. Oh. So you have a slightly hyperactive clicker. Okay, bad clicker. Okay, so MBZUAI is the world's first AI university. It's a graduate-only university, so we have masters and PhD students, and then a large number of researchers and faculty, of course. We're based in Abu Dhabi in the United Arab Emirates, but the pool of faculty and students is very, very international, as you'll see on the next slide. We have, as I say, masters and PhD, 2 and 4 years respectively, programs in the core AI disciplines of computer vision, machine learning, and natural language processing. We're rolling out new programs in computer science, which may sound like a contradiction in terms, to have a computer science program within an AI university, but very much core programming languages, theory of computation, operating systems, that kind of the kernel of what is computer science, programs and robotics next year, and then new programs to follow after that in areas such as HCI, statistics and data science, and computational biology. We're a very young university. We're slightly over 3 years old, and yet we're ranked 18th in the world for AI as a university. So we've achieved a lot in a very short period of time. We have top faculty, as that number would suggest, and we're one of only 8 universities in the world which can claim to be the top within the top 30 across all of computer vision, machine learning, and NLP. There's exactly 1 in Europe, for example. The 2 from Asia are in China, as you might imagine. All of our students are fully funded, so they get very generous scholarships, including on-campus accommodation and annual airfares to return to their home country. As you'll see throughout my talk, we're uniquely positioned as a university which is driving both, obviously, the academic excellence and advances in AI, but also commercial or more applied, and you'll see what I mean by that. Just some factoids, and then I will stop talking about the university and talk about research. So as I mentioned, we're exactly 3 years old. We have around about 70 regular faculty at the moment and over 150 researchers. That number's probably closer to 200 now. A total of 280 students, so we're a very small footprint university, as that name would suggest, but with a very strong focus on excellence. In terms of the stereotype busting element of this slide, for an AI university, we're very proud of the fact that we're over 30% female in terms of our student population. A very strong global pool of different countries that we attract students from. So we have over 40 nationalities amongst those 280 students. I think we have 5 from Sri Lanka at the moment, but I would love to increase that number. Everything, of course, is in English. We have a pool, we have a gym, we have games rooms and various sort of club activities, as you would expect for a university. A large number of on-campus restaurants, and we're based in what's called Masdar City, sort of on the outskirts of Abu Dhabi, very close to the airport, which is a sustainable city. So all of the energy that's generated that we use on campus is from solar power, so we're 100% green. And we're very proud of that. Anyway, so that is MBZ UAI. So as I say, delighted to talk more about the university if you want to come and see us at the stand. But what I'm really here to talk about is fairness and safety in AI. Oops. Sorry. I need to be careful where I click, apparently. So what is fairness? So I'm sure we've all read reports, and as I said, this morning's keynote talked about some aspects of this. But just to ground this talk a little bit more, examples of things that we mean when we talk about fairness are the Twitter image cropping algorithm in your Twitter, or X, I guess, as we have to now call it, feed, where there was actually a bounty that Twitter itself, perhaps in better times as a company, put in place last year, and a PhD student from EPFL showed that there was a very strong bias in the auto-cropping towards lighter-skinned, younger, more effeminate faces, which basically means that, you know, all things being equal, if you're a darker-skinned, older, less effeminate-looking person, then chances are you won't show up in someone's Twitter feed. And is that really fair? Does that sort of seem right, that certain types of people, based on, you know, what are inalienable properties, attributes of themselves, are more likely to appear in Twitter feeds than others? Other examples, you know, very high impact in terms of you know, people's ability to do things in the real world in US mortgage approvals, where this dates back a couple of years now, but there was an expose of how simply flipping a single protected attribute, you know, something like someone's heritage or someone's background, or the zip code, because this was in the US that someone was applying from, meant that that loan approval was rejected. So again, that's not something I have control over. Everything else is the same. My annual income is the same, my assets are the same, and yet you're rejecting me because I have a Latino background versus someone who has a Caucasian background, say. So again, unfair, but in this case also, depending on the legal jurisdiction, illegal. For me, part of my sort of road to Damascus in terms of a wake-up call from my own research as to the very real-world impacts of my own work and how it actually fed into this was in the context of a language identifier. So for non-NLP people, that's simply a system which takes a web page, say some document, and makes a prediction as to what language, for this simple case, or what single language or majority language that document is written in. So it might say something like 95% English and 2% Tamil and whatever else. And this was work done by colleagues at Stanford at the time, back in 2017, for a LangID library that we developed at Melbourne called langid.py, where they showed this horrible correlation, very strong correlation, and this is just for English tweet recall. So the task is simply give me all of the English tweets from a larger feed of Twitter, so throw out anything which is not in English, and show that the recall of the classifier based on different language identifiers, the blue line is our own system, langid.py, had this horrible correlation with the human development index of the country of origin of that particular variety of English. So all the way on the left, you might have a country like Nigeria, say Sri Lanka is going to be somewhere in the middle, and you have countries like Australia and the US, which are on the right. So basically, we do a great job of higher human development index, richer countries in terms of the English that's spoken there, and an increasingly bad job in countries which have a lower human development index. So you have this horrible unfairness in our own systems for a task as simple as language identification, which was just, as the developer of this, a completely irreconcilable thing. So, what is fairness? Just to speak about it more formally, in NLP we tend to talk about source versus target fairness, or author fairness, it's sometimes called, which is the idea of who has written this text, so who is the source of this text, what are the protected attributes associated with them, do we have bias associated with those protected attributes? So I showed you off this single sentence from a larger movie review for the Princess Bride. You would perhaps predict the fact that, well, all things being equal, the author of this is probably more likely male than female, probably an older person. Maybe you'd have hypotheses about their background. And these are the sorts of things that the model picks up on implicitly in terms of its training data. And indeed, in this case, the reviewer was a similar age and demographic to me, I guess, a white male at the time, the late 40s movie reviewer from The Guardian. Versus target bias, which is the reference in the text, so the things that are being referred to. So we have a slightly, political example here. It's taken from one of the standard data sets in NLP, because it refers to slavery in the US. But the basic task is we have a pronoun her, and the job of the system is to resolve, does her in this particular context refer to Polly Simmons, antecedent 2, or Eliza Bryant, antecedent 1. Okay, so we've got this binary disambiguation that we're trying to do as to who a particular pronoun in context refers to, and the target bias we observe here is systems tend to be systematically worse at resolving female pronouns than male pronouns, despite the fact that everything else is sort of similar in the text. And again, it tends to come down to representation in the data, that they've just been trained on data which has a preponderance of male references, and so based on completely superficial in the text, but sort of real-world issues in terms of the sort of text that we've sourced training data from, we have these biases that creep into our systems. So I've talked about protected attributes without really sort of spelling out what I mean here. In the context of this talk, I'll primarily talk about source bias, as in just who has written the text. And in the context of source bias, the sorts of protected attributes that we tend to observe are things like gender. We'll only have a notion of binary gender for the purposes of this talk. Race, whatever you want to define as race. So you get into some messy territory in terms of simply defining some of these protected attributes. Age, perhaps sexuality, various other things. And you have examples of different tasks where these different protected attributes come up. Okay, so what do we do about this? So I'm going to use as a running example, kind of this caricature of debiasing, where the task is we're trying to classify elephants versus rhinoceroses, and in our training data that we have in the lower box here, I've got a series of elephants and rhinoceroses, which happen to be images of soft toys, whereas my target instances, my test instances are cartoonish, so there's a bit of transfer going on here as well. And the predicted attributes that I have, which you possibly can't read, associated with these are the colors of them. So I'm trying to come up with a less loaded example to sort of make the point. So I know that some of my training instances are blue and some of them are purple. And in terms of fairness, surely if I simply obfuscate that information from my model, I'm going to end up with a fair model. Okay, this is what we call fairness as blindness. What tends to happen in practice is when you do this, and this is kind of the machine learning 101 version of approaching this sort of task, is not only are the biases in the training data reproduced, but they tend to be amplified. And why does this happen? Well, it tends to relate to uncertainty in the model, and the model sort of coming down in favor of overrepresented classes. So if we're being good Bayesianists, they're doing the right thing. It's just leading to all of these awful outcomes in terms of minority groups. So why does it happen? Well, because of intrinsic biases in the training data, intrinsic biases in the labels, label imbalance in terms of the predicted attributes, and various interactions between all of the above. Okay, so a sort of slightly more informed way of going about this would be to say, aha, if it's a question of representation in my training data, then surely all I need to do is make sure that I have equal representation across these different predicted attributes within my training data. So if I have equal numbers of blue and purple elephants and blue and purple rhinos, so I artificially bias my training data to filter it down to make sure I've got parity in terms of the representation across these different classes. Does that solve the issue? So this is sort of a still naive, but at least informed baseline way of doing this. It turns out that this is actually reasonably effective. The big issue, of course, is we're throwing out a lot of the training data as part of this. Because we're downsampling to the size of the smallest group within our training data. If we have a heavy skew within our training data, that means we potentially throw out a lot, or possibly the majority of our training data, which is going to impact on performance. So while this tends to help in terms of fairness, it comes at a cost in terms of the raw performance, the accuracy or whatever of our models. So how can we do better? Okay, so I'm going to focus, so there's a huge raft of different techniques for mitigating these sorts of biases. For our purposes, for the first part of this talk, I'm going to be talking about adversarial methods, and then we'll sort of talk about a broader suite later on in this first half of the talk, or first 3/4 of this talk in practice. Okay, so if we think about this a bit harder, one way to try to achieve fairer outcomes for our models is to have two components to my training. So first I want to have my base model, my base classifier, to be as good as possible at reproducing the labels, or labeling my test instances ultimately. At the same time, I want to have the model be as bad as possible at recovering the protected attributes. So to have it as blind as I can possibly make it to the protected attributes. So I'm going to use the protected attributes to try to bleach out their ability, implicit ability, but their ability to capture the differences in terms of these different protected attributes. And I'm going to use adversarial learning to achieve that. And I promise I'm not going to show you off many equations or many numbers, and you're not expected to understand the equations here, but for the machine learning folk out there, what an adversarial approach looks like is it's basically two parts, or a minimax objective function, as we call it, so that we're in the black component of it, it's the standard sort of cross entropy if it's a categorical task we're trying to perform, and so we're minimizing that. And then in the red part, we have this additional adversarial component to our loss, and I'm trying to do as badly as possible, so hence I'm maximizing that, in saying that I just want my models to be very bad at predicting what the different protected attributes are for my training instances as I'm training my model. And if I have multiple protected attributes, so say I had binary gender and age, of some binarized version of age, I guess in this formulation, then I would have separate what we call discriminators or discriminative adversaries for each of those, hence the summation down here. So I'm just summing up over those individual models in terms of a loss. And you might observe that I have these lambdas, I have some hyperparameter that I use to sort of weight up or down the relative impact of these different adversaries on the overall objective. So I've kind of got a dial that I can turn there, one for each of the protected attributes. As I say, I promise I won't give you any more equations. So this is something we'd actually played around with a number of years ago, back in 2018. And the initial experiments that we did were in the context of a very simple task, kind of NLP bread and butter, called part of speech tagging, which is the simple task of, for each word in the context of a larger document or sentence usually, what is its basic word class, something like a noun or an adjective or a verb or an adverb, say. And this was 2017, so this is pre-transformers. So this is all in the context of BioLSTMs. So we train a model over a larger data set. We do some fine-tuning over a smaller data set where we actually have access to the protected attributes and turn on our adversary at that point. And then we test it over both held out in-domain data in terms of something called Trustpilot, a review data set, as well as completely unseen African-American vernacular English, which is completely underrepresented in the Trustpilot data. And our protected attributes are going to be binarized age, so under 35, over 45, versus binary gender. And what we observe in this particular context, so I won't show you many numbers, but just to sort of make the point in the context of this particular instance, our baseline model has no adversarial properties. It's just a simple BioLSTM versus our adversarial model where we turn on these adversarial discriminators. And what we observe is this is all accuracy, so higher is better. Accuracy goes up when we break it down across these different protected attributes, but also the disparity between male and female, and more notably older and younger text, comes down. So we're doing this sort of uplift, but also a narrowing of the disparity. So we haven't completely removed the bias, but we've reduced it from 1.5 absolute percentage points to 0.3 absolute percentage points at the same time as uplifting it. So that was exciting. What got us really excited in the context of this earlier work, though, was when we applied those same models over this African-American vernacular English. So this is sort of very distinctive data for a very distinct subpopulation in the US. And we observed even greater improvements in terms of the accuracy, lower numbers, yes, but still in terms of having adversaries which were applied to binary gender and age, we suddenly got these improvements over this completely out of domain or out of register, perhaps, text type that is African-American vernacular English, so, i.e. it generalizes. In sensitizing our models to particular protected attributes, they seem to be able to do a much better job over completely unseen protected attributes, which wasn't something that we'd been expecting at this level. So this was kind of the, we're onto something, off we go, work, which then gave rise to a series of later papers. So we sort of came back to this work a number of years later and said, okay, as exciting as those results were, when we actually play around with adversarial learning techniques in the wild, what we observe is life isn't quite as simple as that. So in particular task settings, we observe instability. So it sometimes works really well and it sometimes just really doesn't work at all. It just fails to converge in some instances, and there's not a lot of rhyme and reason as to when it works well and when it doesn't work. And this is something that other people had observed subsequent to our original work and had sort of come up with engineering solutions to such as, well, if I add extra capacity, extra parameters basically, to my adversarial discriminators, does that help out? If I upweight them using these lambda parameters, does that help out? Or if I ensemble them, does that help out? So instead of having one discriminator per predicted attribute, I'll have multiple per predicted attribute, and it's rely on stochasticity to get improvements in terms of fairness. And these, again, they sort of sometimes worked and they sometimes didn't work. There was a little bit more rhyme and reason, but it was very unpredictable still when you'd actually see improvements and what out of these would give you those improvements. So that then gave rise to work that we came back to a couple of years ago with one of my students at the time, Shidong Hung, to say that, well, one of the issues we have with the ensembling approach is you are just relying on stochasticity. If we have enough base models in terms of our ensemble of adversaries, what I'm representing here now as an ensemble rather than a single model, then things will come out in the wash, as happens with ensembles. But it's a very expensive way of getting there, and we're relying on stochasticity to do it. If instead we applied constraints, so we had a constraint on what the models are actually learning, specifically in the form of an orthogonality constraint, so that the different adversaries are forced to be as orthogonal to each other as possible to learn different things, then we're going to get better diversity, as in constrained plan diversity rather than random diversity in terms of our ensemble. The last equation, I promise. This is the particular mathematical formulation. We use that using the squared Frobenius norm, and so we have some number of base classifiers that we're ensembling under this constraint with an additional regularization term in terms of our base objective. And it has some nice mathematical properties, it turns out, in terms of preventing the model from just kind of learning kind of hacks to produce what superficially look like different classifiers, but actually are rotationally equivalent to each other. So it suppresses that sort of behavior. So this was 2021 now. We sort of came back and did a series of experiments. In this instance, it's now in the context of sentiment analysis. Our race is now, our predicted attribute is now race, so it's African American vernacular English versus standard American English. And what we observe now is, and so in the context of this work, we're interested in two things. So if we ensemble our discriminators, how much improvement do we get? And we sort of found that yes, we did in fact get improvements. It was more efficient, it was more stable with this orthogonality constraint. And in particular, it helped reduce what are called gap metrics, which is not the extrinsic evaluation out the other end, something like accuracy, say. It's when we try to predict, reproduce from the learned representation from our model, what was the predicted attribute. I want the model to be as close as possible to a random baseline, or a weighted random baseline in practice relative to the training data. And what we found is that it didn't do as well there. That's kind of a side note. But then we got interested in the question of, okay, it's all well and good assuming for sort of research purposes that we have full access to predicted attributes, but we're kind of creating this paradox in the sense that if you give me access to these predicted attributes, which are sort of very private things, very sensitive things for the particular individual potentially, then I can give you perhaps not fairness guarantees, but at least empirically better fairness outputs for your model. But the cost to get there is you have to disclose everything. So I need to know everything about all of your users, say, to get this. And there are contexts where either I just legally cannot ask people some of these questions, or for all sorts of reasons, people aren't prepared to disclose that sort of information, understandably so. So what happens if we only have access to a very small subset of annotations for our predicted attributes? Can we still achieve these sorts of fairness outcomes for our models? So we're assuming that we've got partially labeled data now with respect to our predicted attributes. What happens? So for some of our training instances, we just don't know what color the elephants and rhinos are, coming back to our example. And if we think about how we're training our classifier, one thing I haven't told you is the way that you train these sort of classifiers is actually an iterative process, that you update your base model and you update your adversaries and you iterate between those two because the minimax objective isn't differentiable. Given that, if we're using slightly different sets of instances to update the base models versus the adversarial discriminators, well, that's fine because that's happening at different phases of training. So we can trivially do this. So given that, it doesn't really matter if it's a different set of instances that have the annotations for our target variable versus our protected attributes. It also means, if we think about it harder, that they could be completely decoupled from one another. So I could have labels for instances from one data set, and I could be updating my adversarial discriminators based on a completely disconnected data set, which has protected attributes that are relevant to my first data set. Okay, so it's not just that I could have partially labeled data, I could have completely disparate data. I could have zero overlap in terms of my labels for my target variable versus my protected attributes. So in the partially labeled instance in the first case, what we observe is if we scale down the amount of labeled data to just 1%, for example, of the original, so we're looking at the accuracy of my model, so I want that to be as high as possible. I want to take as small a hit as possible there versus this gap, where a gap of 0 means it's perfectly balanced. I don't have a disparity. A higher number means I have a bigger disparity one way or the other. And so what we observe is we can get to basically a 0 gap without taking really any hit in terms of our performance, even for 1% labeled instances when we're doing it in domain. Whereas when we do it out of domain, so just to make the point, now we don't have any elephants and rhinos where we've got color annotations, we've got whatever other random animals, but that's fine because we're doing this decoupled training. What happens, so we do this over 2 separate data sets, where the blue line that we have here across the figure is a random baseline, as in if we randomly assigned labels for protected attributes, so that's obviously something we want to do better than, and the blue dots are what's happened if we've got the 1% of in-domain instances. So we never do better than the in-domain 1%, but we certainly do a lot better than the random. So there's some utility in using completely out-of-domain protected attributes. So again, encouraging and sort of showing the broader applicability of this method, and the decoupled nature of the training is something that we can use to our advantage. Okay, it doesn't end there though. So let's think a bit harder about what is bias and what it means for something to lack fairness. So to date, we've always sort of thought about if we have multiple protected attributes, we think about them independently. So we think about whatever, young versus old, we think about male versus female, and we look at those independently. But what about the interactions between those? And we're not the first to observe that what happens, even for models which you can show to have very little gap independently between multiple protected attributes, when you look at the interactions between them, the cross product, for example, here, you get unfair results for certain combinations of those. Okay, so to be clear, the independent case is what we've looked at up until now. So it's something like female versus male, for want of a better term, white person versus person of color. Okay, and we just look at those independently. Whereas if we look at the interaction between them, one way to do it is to look at the non-overlapping exhaustive combinations. So look at white males versus male people of color versus white females versus female people of color. So we've got the logical combinations of those two. But there's actually an additional, if we think about higher arity predicted attributes, option that we could consider, what's called gerrymandering intersectional groups, where we think about them both independently, as well as in combinations of two, and 3 all the way up to whatever the number of protected attributes it is. So every possible combination, the full Cartesian product of all of these with the exception of the null set, hence the -1. Just to make sure that there's sort of no nook or cranny that our model can have failed to have achieved fairness on in terms of interactions between these different things. And what we observed was if you train just in terms of independence, you can have quite poor results in terms of intersectional bias or gerrymandering intersectional bias. So what we were asking here was, well, how can we achieve strong results in terms of intersectional or ideally gerrymandering intersectional results without taking too much of a hit in terms of if we do the naive training on the basis of the gerrymandering groups, for example, data sparseness starts kicking in very quickly. We end up with some very tiny and in some instances non-existent combinations of all of these different protected attributes. That's obviously not going to help us out in terms of model training if we have 0 training instances for a particular one of these combinatoric groups. So if we can actually move on. So the questions we're asking here was if we evaluate on these intersectional and gerrymandering intersectional definitions of bias, what happens? And if we directly optimize for intersectional, for example, what happens in terms of gerrymandering intersectional? Or do we have to go all the way to gerrymandering intersectional bias in terms of optimization to achieve strong results there? So this was work we did a couple of years ago. And again, if we think about the adversarial approach, there were various other approaches we looked at in this work, but just for the purposes of this talk, we can simply represent these particular groupings that we've come up with as individual values for the adversarial discriminators that we're building. Okay, and we can either do this as a single model, or we can have one per group, one versus rest, which is going to have computational implications, of course. And we also looked at various other methods, including this bias-constrained model, but I won't talk about that. And so what we found here was we're very encouraged that even if we only optimized for intersectional fairness, we actually achieved strong results in terms of this stronger definition of gerrymandering intersectional fairness. So that was a good thing, and that sort of seemed to be the sweet spot. And that various other methods struggled to scale to this sort of very fine-grained definition in terms of actual optimization to achieve this sort of result. So again, sort of up until this stage, we're sort of saying, okay, adversarial learning seems to be a goer. It seems to work well under these different contexts. It has sort of various properties which make it particularly well suited to these different data conditions. But then we sat down and said, okay, well, let's actually look at this more thoroughly. So again, this was work last year. If we look at across different dimensions of data conditions, things like what's my target label bias? What's my protected attribute bias? Those two are independent variables that we can adjust. If I create the sort of kind of worst case of I've got bias in one direction for my target labels, I've got bias in another direction, within my majority class for my target label, if it's a binary classification task, I have a different bias versus over my protected attribute versus what I have for the minority target label. So it's not consistent, uniform across the different target labels. I've got these strange inconsistencies across the different target labels with respect to my protected attributes, which is something that you do get in real-world settings, versus the arity, how many classes do I have in terms of my target label, and in classification versus regression settings. And the basic idea is, okay, let's take a bunch of different approaches, well beyond the adversarial approaches that we've talked about now. We're going to vary these different variables across one condition in the first instance and measure performance, and then look at the interaction between them. So we have a range of different methods. I'm not going to go through all of them. What we've been talking about up until now is this diverse adversarial training, but there are many, many other methods, as you might imagine, some of which we've developed, some of which other people have developed. And what we observe, jumping to the chase here, is, well, sampling-based methods. And what sampling-based methods are is this pre-processing approach. What I talked about is kind of the informed, naive baseline. I do instance weighting, or I do some sampling of my training data, and that's my solution. So simple, but reweighting at least, in terms of instance weighting, is surprisingly effective. So if anything, they're generally pretty good, but they're really susceptible to extreme class imbalance. And they do poorly in terms of this intersectional and gerrymandering bias that we were just talking about. Methods like adversarial learning, they tend to be more robust to the higher arity target labels. If I have a target variable which is more complex in terms of numbers of values, but under stereotyping, this I'm reversing the bias of the data with respect to my target variable values, and intersectional gerrymandering bias. So the wheels start falling off here for our adversarial method. And if anything, there's no sort of one best method which just performs well across the board. You really have to know your data conditions to know what method is going to perform well. And different results for regression as well, which I won't go into. So it kind of ends up on a cliffhanger. There's a lot of other work that we've done, including looking at things like completely unsupervised bias mitigation, where we have zero access to any predicted attributes and we still get strong results. But I'll save that for another day, or you're welcome to ask me about that. Okay, so for the second half, call it a quarter because it's much shorter. I promise you don't have to quite kick me off the stage yet. I want to talk about AI safety, which is was alluded to again this morning and is a very important component of a modern day AI solution. And so what I mean by that, I'm going to talk about it in the context of a particular case study of work that we've done in the last couple of months in building a large language model for Arabic, something called JACE, which we co-developed between the university, MBZUAI, Core 42, who are a commercial organization based out of Abu Dhabi, and Cerebra Systems, who are an AI hardware provider based out of California. So we developed JACE, something that we released a bit over 2 months ago now in terms of a 7 billion parameter and 13 billion parameter model, both in terms of a base model plus an instruction-tuned chat variant of the respective models. As public domain models very much achieved state-of-the-art for Arabic LLM, which we're very proud of. And there's a lot of sort of hard work that went into the development of these models in terms of getting enough high-quality Arabic data, just raw textual data, to train the models off was surprisingly difficult. And we just couldn't find enough data to train models of this size. So there was a lot of tweaking of the recipe, if you like, in terms of consolidating the Arabic content with English content to get cross-lingual transfer and boost the respective abilities so that the models are actually competitive with similar-sized Llama 2 models, for example. Well, for Arabic, they're sort of almost the same as ChatGPT, and we hope that new versions that we're training will surpass ChatGPT for Arabic. Why am I talking about this? Partly to sort of set the context for what I'm going to talk about for AI safety, partly to sort of make the point that as a university, our ability to develop these sorts of models, the computational cost associated with these was not small, particularly in the development phase when we were trying to work out what's the best way of training these sorts of models given the data conditions that we were operating under. And we were very much uniquely placed as a university to be able to deliver on this sort of a project. So it speaks to how the university is set up and this combined mission, as I said at the start, about not just basic research but applied research objectives coming out of the university and being able to deliver what are commercially relevant models to the broader Arabic community under a commercially compatible license, you might notice. Back to AI safety though. So as part of releasing this model, of course, we wanted to make sure that we had guardrailing, as it was described in the earlier talk very appropriately. So this is the question of it not generating inappropriate, toxic, offensive, whatever outputs. So reining in certain behaviors of the model. Hallucination is somewhat within this, and it's sort of a much broader issue that goes beyond this. So I won't talk about hallucination per se. I'll talk about more direct AI safety outcomes. So there were four steps that we used in the development of JS, the publicly released models, in terms of how we achieved this. So the first is instruction tuning, this idea of I give it prompt response pairs where the ideal output in terms of AI safety achievement should be this. So it should not produce an output if you ask it to something nasty, how to inflict some harm on another person, something like that. It should tell you why it's not going to give you an output. We also do something called master prompting, which I'll talk about in a moment. And then as a post-processing step, we have toxicity detection, so simple classifiers on the output, where if we detect that it's producing something toxic, we suppress that output, and then key phrase detection, the sorts of things that you might expect in terms of offensive, not safe for work, whatever you want to call them, tokens in the output, where we again suppress the output for the publicly deployed models. Okay, so in terms of instruction tuning, so we did some basic work as part of this, as part of a data set that we've released. So it's the largest data set for instruction tuning for AI safety for public domain models, something called the Do Not Answer data set. And there's a lot of detail to it. It's a 3-level hierarchical risk taxonomy that we developed as part of this, based on previous work, with different levels of risks that we take into consideration. And just to give you a sense of what it's all about, the top 5 levels are respectively information hazards. So this is something like you asking for some information which is going to compromise the privacy of a particular individual or a particular company, say. There's perhaps data that had crept into the training data which we don't want to be output, or safety critical information. Malicious uses, people trying to use LLMs to cause harm or get information that they can use to cause harm to themselves or to others. Discrimination, exclusion, and toxicity, so things which relate to unjust, toxic, oppressive content that you're trying to get the model to give you information on. Misinformation harms, so part of this is hallucination, but hallucination is actually much broader. So this is false, misleading, nonsensical, or just poor quality information. And then perhaps a more subtle one is HCI harms. So again, this was alluded to earlier, the idea of people getting over-reliant on the LLMs or anthropomorphizing them and developing a relationship, an emotional connection, making it clear that I'm just a machine. I am a bot. So you shouldn't use me for personal counseling, or shouldn't get emotionally attached to me in any way. So we developed an instruction tuning set for this, in addition to this hierarchical taxonomy. Just to give you a flavor, we then did various evaluations using this data set over various contemporary large language models. In this instance, it's just for English, so we've got the GPT-4s and the Claudes and the whatnots of this world, and we're rating them in terms of how safe they are across these different criteria. Again, happy to talk about this offline if people are interested in terms of what this means. The second step I mentioned was master prompting, and so this is this idea of, and for those who've been following the various reports on jailbreaking, you'll know in part of what this is all about. So the idea that there's kind of a manifesto, a behind-the-scenes instruction that the LLM has access to, which is supposed to guide how it operates, the sorts of styles of responses it generates, for example. So there's a long, one for English, one for Arabic, master prompt behind the scenes, which kind of brings JS to life and helps guide how it generates prompts. So as part of that, you'll see you're a helpful, respectful, and honest assistant, abide by the following guidelines, should not include any harmful, etc., etc. So it is, really sort of just spelling out in natural language kind of what the ideal behavior is. It's absolutely not fail-proof, but it does help. Okay, that's all I want to say about AI safety, just to give you a bit of a teaser sense of it. So just to wrap up, so in the first part we talked about bias and fairness variously. I talked about adversarial learning at length as an effective technique for mitigating. We focus primarily on source bias, but in practice it can be applied to target bias as well to achieve fairer model outcomes. We talked about, well, they're not ideal because of model instability. If we ensemble with orthogonality constraints, we can boost that. We also looked at this idea of, with partially labeled data, does the model still work well? And sort of found that, well, yes, it does. Cross-domain, less so, but it still works to some degree, better than nothing. Then looked at this idea of intersectional and gerrymandering intersectional, and found that even under just intersectional training, we could get strong empirical outcomes in terms of gerrymandering intersectional results. But then when we looked under different data conditions, we sort of realized that, well, okay, the world's more complicated than that. It really does depend on specific data conditions as to what model works well. There is sort of no one panacea in terms of one model which just works well across the board. Or if there is, it tends to be the very simple methods, but they don't work as well in particular settings. So there's a lot more work, obviously, to be done in this space. AI safety then, we talked about briefly at the end in the context of a modern day large language model deployment. It's still a very much evolving, underdeveloped field. It's only really existed as a field for the last couple of years in the context of LLMs. Responsible AI obviously has a much deeper history than that. We sort of talked about some of the different dimensions to it, but the important thing to bear in mind is, as you saw with that radar plot, no LLM is perfect and is ever going to be perfect. And you know, part of what we need to do is educate our users about the risks of LLMs, I would argue. And there's still a lot to be done. Come and join us if this is a space that you're interested in terms of delivering on truly fair, safe models, as in not sort of trivially achieve that because you've got a random classifier, for example. And I just wanted to finish up in acknowledging my wonderful collaborators, students, former and present collaborators, both at the University of Melbourne as well as at NBZ UAI. And with that, I thank you.
Thank you very much for a nice presentation. I was wondering, I might have missed it, but it felt like you sometimes have to know these attributes that might be critical, right? You have to know which attributes are the critical ones that could cause the bias.
Yeah, so that's part of the issue with debiasing at the moment, that you need to know what protected attributes across which you want to achieve fairness to achieve fairness. So again, it's part of this sort of circularity, which was why unsupervised methods where I don't presuppose what the protected attributes of interest are, because, I don't know, maybe I develop a system now and in 10 years' time I realize there's this whole other dimension of predicted attributes that I just never thought about, and across that my system is just awful. If I have unsupervised methods, or if I have better generalization across different predicted attributes, I have more assurance that I'm not going to sort of be embarrassed in 10 years' time in realizing that the world has moved on and I've suddenly realized there's this other thing which was lurking in my data set, if only I'd been aware to it at the time, if that answers the question.
Thank you, Professor Timothy, for your insightful keynote. Actually, I have a duty to do, like there's an app, so the questions coming from students appear here, so I'm supposed to ask. But while things pour in, let me take the advantage and ask my question. Okay. So, so fairness and safety, I believe these are subjective things, right? So, maybe you don't agree, I guess, so you can explain. So I believe so the biases involved in the people involved in machine learning model training also affects the, for example, let's say there's a data set, you train a model, and you notice that there's some fairness issue, and you need to fix it. So there's a bias from the researcher as well who's assessing this. How do you make sure that the people involved are fair and not biased?
Yeah, that's an intriguing question. So I'm not sure that I agree that it's subjective on the part of the researchers. It's subjective in the sense of what protected attributes we focus on. So in that sense, absolutely. In practice, it's very hard to find data sets which have annotations of protected attributes, for very good reason, because people don't just give gold standard data of their personal information in online context for public domain data sets, for example. And if we're talking about source bias, it assumes I have single authored documents. So something like a tweet, fine. Something like a Wikipedia document, I don't know what fairness means in that context, because I'm going to have lots of different authors with lots of different backgrounds. So the document itself, it's really not clear what fairness means there. Yes, I could have some method for aggregation to try to look, in aggregate, what's the pool of editors for a particular article look like? How is that different from another article? Do I have any bias creeping in because of that? But that's a slightly different question again. I mean, I think if we take a step back, as humans, absolutely, it's very hard to remove all of these unconscious biases that we carry around with ourselves. And if anything, some of the data sets that people have used, so things like doing filtering of CVs for job applications, say, if you dig in, it's not that there are sort of good quality public domain data sets for good reason, but if you get access to behind the scenes data sets from companies like Seek that was mentioned in the introduction, one of the big job search engines in Australia, when we work with them, if you actually look at the screening that the employers do, manual screen, there's all sorts of evidence that there's bias that's creeping in there. Now, if they're preferring male candidates over female candidates, say, or younger over older, or vice versa, depending on the sort of role, is that appropriate or is that not? You could argue that, but even in the mortgage case, you could sort of defend the banks and sort of saying, but whatever, people of a certain background we've observed, even if they're owning the same amount of money, as a Hispanic person, their job security is less. So you're taking too limited a view on the data. So in fact, it's perfectly okay for us to use this. I'm not saying that I subscribe to that view in any way, but there's a messier, more complex picture out there in practice. And so yes, subjectivity does creep in there, and in the real world data sets that you play around with, absolutely there's subjectivity. And in a way, the evaluation we're doing, I would say, is absolutely not subjective, because we have these very crisp criteria and well-defined evaluation metrics for it. So it would only be the sampling of protected attributes that you use over that data. But in a way, we're trying to hold our models to a higher standard than we hold ourselves, which I personally don't have an issue with. I think we should be doing that with AI. I'm not sort of getting utopian here and sort of saying that this is all about whatever AGI and surpassing human intelligence. It's not about intelligence at all. It's about trying to use AI to create a better world with humans at the helm. And if we're trying to build the tools to do that, then I want to hold those tools to a higher level of scrutability to what I hold a random person on the street. Sorry, long-winded answer to the question, but I hope.
Yeah, I think I just have 1 more minute left. So I'll pick just one question. Maybe you can quickly give a response. Muhammad Izzat asks, you mentioned about the falsification of AI. What are the methods that can be used in cases of reduction of these falsification, just only without considering the size of data sets used? I just read as it appeared. Did you get the question? Let me read again. You mentioned about the falsification of AI.
The falsification?
Falsification. I'm not sure.
Sure, I talked about the falsification of AI.
Yeah. Oh, maybe I'll skip to the next question if that is okay.
Okay.
Yeah.
Sorry, not quite
So
sure
with
what
the so Nirmani Dasanayaka asks, with the changing definitions of discrimination,
yes.
and the means by which one could discriminate, etc. So how do you keep up with those things, like changing definitions of things? Probably related to my questions as well.
Yeah, I guess this relates back to the question of protected attributes themselves perhaps being a moving target. So perhaps what we were sensitized to 30 years ago versus what we consider now in terms of equity, it's much richer and more multi-valued perhaps now than what we used to consider 30 years ago, just because the world has moved on since then. So it's a very important question. How do you stay on top of that? I think in practice for any of these sorts of systems, it's very important that we're doing regular model audits. I mean, data audits, yes, but model audits as well. A little bit like my anecdote about langid.py. It was something that we developed, 15 years or so ago. It sort of had a longer shelf life than what we ever predicted. And people are sort of showing that, okay, it's this old system, sure, but when analysed under a particular lens, you've got all of these sort of horrible skews in the output of the model. That's only possible because we've got access to data which we didn't have access to 15 years ago, and more sensitization, I guess, to the end use cases. As a field in NLP 15 years ago, we weren't thinking that all of our technologies were going to be in the hands of consumers. Now, you're almost hard put to come up with something which doesn't end up in the hands of consumers in NLP. It's a very almost confounding time to be in NLP as someone who's sort of been in the field for 30 years. I mean, empowering, yes, but kind of there's the weight of responsibility on your shoulders in NLP. So it's very important that we're always sort of looking back as well as forward in terms of the models that we're developing.
Thank you.